Hello, everybody. So welcome to week 3, lecture 1. What we're going to be covering today is going to be analytic limits, piecewise and continuous functions. Basically, what we did last week is we learned about the concept of limits, and we learned how to look at them on a graph, and we learned how to find them using a table of function values. But what we did not do was actually calculate limits in any kind of formal way, or actually, technically, we never even calculated any limits at all. We just guessed at what the we just guessed at what the limits would be based on what we saw in our table or what we saw on a graph. So this week, we're going to learn how to actually calculate or to evaluate limits. This is going to be a few lectures before we're through with this section. And so this first section is just the first part of section 2.3 in your book. And we're just going to try to pick up some of the algebra stuff that you need to know and some of the vocabulary and so on. So this lecture is supposed to help you meet the course learning objectives of SLOA. Stop changing my page. SLOA is to apply the concept of limits, and the two, sub-objectives, I'll call them, are A2, which is we're going to apply the concept of limits by evaluating limits using appropriate techniques and properties of limits. So that's what we're learning is techniques of to evaluate limits and properties of limits themselves. And also, as always, we're going to be making appropriate use of available technology. So we are going to be using technology to help us evaluate limits when appropriate. Okay, that's enough of an introduction. Let us get started. So this says something I've already said. You've learned the definition of limit. We've looked at graphs. We've looked at tables of function values. But now we're going to use algebra to calculate limits. That's what we're doing today. So the first thing I want to talk about are polynomials. Now, polynomials are very basic types of functions, right? You've seen lots of polynomials in your life. Like, for example, f of x equals x squared plus 2. That's a polynomial. It's a second degree polynomial, right? G of x equals 5x to the third plus 3x squared minus 7. That's another polynomial. That's a third degree polynomial. Now, you'll also notice that I've started throwing in this word continuous. Polynomials are continuous functions. What that means is that if you look at the graph of a polynomial, there's no holes in the graph. There's no jumps in the graph. There's no breaks of any kind. They're just nice, smooth curves with no sharp corners or holes or anything weird going on at all. They're just very simple functions. Okay? And something we're going to learn as a property of limits is that if you are ever calculating the limit of a polynomial as x approaches a, all you have to do is plug in x equals a. That's a property of every continuous function. Every continuous function works that way, but we're learning this property first just in terms of polynomials. So, for example, how does that work? Well, suppose you had this problem right here. You wanted to calculate the limit as x approaches 2 of x squared minus 5x. Well, what you would do is you would recognize that x squared minus 5x is a polynomial and therefore continuous. And because of that, all you have to do to evaluate that limit is plug in x equals 2. Right? This is very different than what we did in the previous lecture. In the previous lecture, we looked at graphs or we made tables of function values. Here I'm saying just plug in 2. That's different. So you plug in 2. So you plug in a 2 for x, you get 2 squared minus 5 times 2. So you work that out. 2 squared is 4, 5 times 2 is 10. So 4 minus 10 is negative 6, and that's your limit. Okay, it doesn't even feel like you're evaluating a limit, right? Because you're just plugging in the number. It looks like all we did was calculate f of 2, and that's what we did. This is a property of continuous functions that this number is the same as the limit always. I shouldn't say that. F of 2 is always the same as the limit as x approaches 2 for a continuous function. Okay, so we want to know this first, that you can just plug in numbers to evaluate limits of polynomials. Okay, so weird. Just to make sure we understand this, here are two very quick examples. So example 1, limit as x approaches 5 of 3x plus 1. What would you do? Well, you would just plug in the 5, right? So you plug in the 5, 3 times 5 is 15, 15 plus 1 is 16. And if we look at the next page, it should say that this first one is 16. Yep, there it is. The answer is 16. Now for the example 2, we have the limit as x approaches negative 3 of x minus 1 cubed. So if you were to put in the minus 3 here, you have minus 3 minus 1, which is minus 4, and then minus 4 to the third power, which is going to be 64, negative 64. So I show the math right here. Okay, so whenever you have the limit of a polynomial, just do that. You don't need anything more complicated than plug in the number. Okay, of course, you're not always going to be so lucky. You're not always going to have polynomials. So with that said, let's look at some of our basic limit laws that will apply to polynomials and well, actually apply to everything, but in particular, they apply to polynomials. So our first set of limit laws. So essentially, if continuous functions are added, subtracted, multiplied, or divided, then they're still continuous functions. That means that if you were previously evaluating the limit of a continuous function by plugging in x equals a, you can still evaluate the limit of a continuous function by plugging in x equals a if you multiply two continuous functions together, or divide them, or add them, or subtract them. Okay? That's because subtracting, adding, multiplying, dividing continuous functions results in new continuous functions. The only thing you have to worry about is that when you divide two functions, you might get a divide by 0, right? And that's why in these rules here, which you'll see here, limit of p of x plus q of x as x approaches a is p of a plus q of a. So what I'm saying there is, if you want the limit as x approaches a, you just plug in the a for the p and the q. And p and q are assumed to be polynomials here. Now, if you multiply functions together, same thing. Limit as x approaches a of p of x q of x, you just plug in x equals a, get p of a q of a. If you divide them, limit as x approaches a of p of x over q of x, you get p of a over q of a, right? You're just plugging in a for both of the x values. And then it says if q of a is not equal 0. You can do that in that case. If q of a is 0, this is a divide by 0, and something more complicated happens. Okay, so whenever you have limits, basically for now, especially at the beginning, you're mostly going to be worried about divide by zeros. Adding functions, multiplying functions doesn't really cause any problems. So take a look at this example. Please stop changing the page. So if you look at this limit right here, it says in this example, you can see that plugging in x equals a will not make the denominator 0. This means you can just plug in x equals a like we have been doing before. So this limit says limit as x approaches 2 of 4x minus 1 divided by x plus 5, right? So the denominator is x plus 5. That would be 0 if you plugged in x equals negative 5, right? Because minus 5 plus 5 would be 0. But we're not plugging in negative 5, right? Because this is a limit as x approaches 2. So if you're plugging a 2 into the denominator, everything is just fine. So to evaluate this limit here, all you do is you plug in x equals 2 for all of the x's that you see. And here is the result. So 4x minus 1 becomes 4 times 2 minus 1. X plus 5 becomes 2 plus 5 when we plug in x equals 2. You work that out, and if I didn't screw up the math, then I ended up with 7 over 7, which is 1. So this limit is 1. Okay, so we again were able just to evaluate the limit by plugging in x equals a. We didn't have to do any algebra or anything complicated at all. Just a reminder here, I guess. You can always use Wolfram Alpha to help you evaluate things. So like, of course you can work this out by hand, but you could also just, if you go 4x minus 1 over, what was it? X plus 5. X plus 5. You can always type in something like that, and you can just say at x equals 2. And you can make the computer evaluate that for you in a pretty convenient way, instead of doing all of the arithmetic by hand. All right. So if the denominator is not going to be 0, you have nothing to worry about. So the questions for us are mostly going to be, what happens if the denominator is 0? Okay, so what we're going to be looking at is a case where we're going to be looking at cases where the denominator is going to be 0 if you tried to plug in x equals a, and how do we deal with that? Okay, and there's going to be a variety of different techniques that we use. Basically, what's going to happen is there's going to be 3 different problem types that I'm going to call the fraction type and the root type and the polynomial type. And each of those different types of problems needs its own type of algebra in order to solve it. So what I say here is that I say, of course, sometimes you will have a divide by 0, like this limit here, the limit of x squared minus 9 over x minus 3 as x approaches 3. If x approaches 3, if you plugged in 3, the denominator would be 3 minus 3, which is 0. Also, the numerator would be 3 squared, which is 9 minus 9, and that's also 0. You'll notice in all of these problems that I keep saying that the problem is that the denominator is 0, but you'll also notice that it's not just the denominator, it's going to be the numerator as well. And the reason for that is because if the numerator and the denominator both become 0 at x equals a, then you might have a limit. If the denominator becomes 0, but the numerator is just like a number like 5, then actually you don't have a limit because the function will become infinite. And we'll deal with those when we talk about infinite limits, which is not yet come in this course. So that's why I keep talking about the denominator being 0, but we're looking at fractions where the denominator and the numerator are both 0. Okay. So what we need to do when the denominator is 0 is we're going to try to employ some kind of algebra technique where we simplify the function and get rid of the divide by 0. Because if we can somehow get rid of the divide by 0, then we'll be back in the previous case, right? Like on this last example, there's no divide by 0. Well, what if there was a divide by 0 and somebody fixed it, right? We wouldn't be able to tell. As long as we can get rid of the divide by 0, then we can just do what we did on the previous page and plug in x equals a. So that's always our goal, is we're going to try to get rid of the divide by 0 with algebra, okay? So for rational functions, a rational function is a polynomial divided by a polynomial. So that's what we've been looking at so far. For rational functions, what you're going to do is you're going to try to factor the polynomials and then cancel some terms. And maybe when we cancel the terms, we're going to get rid of the divide by 0, although that depends on the problem. Okay, so this is the idea. We want to get rid of divide by zeros. That's the goal. Okay, oops. So here's an example of where we would do that. So this says to evaluate the limit as x approaches 7 of x squared minus 49 over x minus 7. So you can see that if you plug in x equals 7, the denominator will be 7 minus 7, which is 0. So this will be 0. If you plug x equals 7 up here to this x, you're going to have 49 minus 49, which is also 0. So you're going to have a 0 and a 0 with the denominator, and then what happens there? Well, we don't like that. We don't want the 0 in the denominator because now we can't do the limit. So we got to fix it. So what you're going to do is this x squared minus 49, you're going to factor that. You're going to factor that into a difference of squares. Now you should be comfortable factoring, second degree things. If not, you can use Wolfram Alpha to help. Like I should be able to say factor, what was it? X squared minus 49. And it will tell you how to factor that yourself, or it'll tell you how to factor that. Use that if you need to help you factor. Back here. So we factor that numerator into x minus 7, x plus 7. I guess I have the instructions here. So you factor that numerator, x squared minus 49 becomes x minus 7, x plus 7. At that point, remember that our goal is to cancel the divide by 0. So after you factor, you look at what you're left with. You notice you have an x minus 7 in the numerator and an x minus 7 in the denominator. So you can cancel the x minus 7 out on the top and on the bottom. So we cross those out. After you cross those out, you're going to be left with x plus 7, right? Because that's all that's left when we cancel out the two x minus 7s. So your limit is just the limit as x approaches 7 of x plus 7. After you cancel that out, right, and you're looking at this line right here, limit of x plus 7, there's no divide by 0. And if there's no divide by 0, you are allowed to plug in x equals 7. So you just replace the x with 7, and you get 7 plus 7, which is 14. So do you see how that works? Very simple process. It's just factor the numerator, cancel, then you can plug in x equals a. So you're fixing the divide by 0. That's what we're doing. We're fixing it. Okay. Now, you might wonder what's going on there. Like, how come that works? Why is that not an issue? Well, the reason it works is if we look at the graph here, Desmos, if I were to make a graph, we've talked about Desmos before. So if I go x squared minus 49 divided by x minus 7, you'll notice that that just looks like a straight line. And if we go to, I guess, 7 comma 14 is where we would need to look. Kind of hard to be on there, right? I think you can kind of see that that's going to be 714. Can I make that bigger? Oops. Right. 7 undefined. So you see, you're not allowed to plug in 7 because 7 will be undefined. But you can see that basically you're at 14 there, right? Like 6.95, 13.95. And then on the other side, 7.06, 14.06. Right? So there's just this one missing point at 7. And what we're doing is this algebra that we've done, when we cancel these out, you cancel out the x minus 7s, and you're just left with x plus 7. And if you were to plot that, let me unplot that. If we just plot x plus 7, and you compare this, right? If you compare these two, you see they're actually the same function. The difference is x plus 7, when you plug in 7, actually exists, right? On the blue curve, you get 7 comma 14. On the red curve, you get 7 comma undefined, right? These are really the same function. The only thing is that the first one, x squared minus 49 over x minus 7, has a divide by 0 at 7. So there doesn't exist. And that's what we're fixing. So when you factor and cancel, you're getting rid of that denominator there. And what you're left with is really just pretty much the same curve. It's the same curve, except it does not have the hole. Okay? And so you cancel your divide by zeros, and then you get a number. And that's all we're doing here. And we're going to talk about that more in the next lecture, by the way. This is one of the 3 techniques that you need to know. The other thing I want to talk about in this lecture is going to be piecewise functions. So this is a topic that you should have studied a little bit in a pre-calculus class, or at least you don't really need to have studied it, but you kind of need to know what's going on. If you've got a piecewise defined function, like this one that I've written right here, you need to understand what it means. So this says f of x is equal to 3x plus 2 if x is less than 4, and 5 minus x if x is greater than or equal to 4, right? So this is in 2 pieces. You use the first formula for x values less than 4, and you use the second formula if x is greater than or equal to 4. And you can easily graph those in Desmos if you want. You kind of have to know how to do it. I'll write it right here. So like, for example, here's how you would do it. You could say, I already forgot what it was, 3x plus 2. Like if you say y equals 3x plus 2, there's 3x plus 2. But if you only wanted x less than 4, what you do in Desmos is you open curly braces, and then you'd say x less than 4. Like that. And then it stops right there. Also, you don't have to do this, but if you wanted to, I can see that that's at 4:14, 4 comma 14, 4 comma 14. So a lot of times what I'll do if I'm graphing it is I will put an empty circle there like that. So that's less than 4, x less than 4, right? Because 1, 2, 3, 4, 5. So this is 4. The other piece of the function is 5 minus x if x is greater than or equal to 4. So you can plot that as well. You can say y equals 5 minus x. But not this whole thing, only when x is greater than or equal. So I hit, the way you get that is I type greater than, and then if the next thing I type is equal, it turns it into an equal sign. And then I can put the 4. Close that. And there you go. Also, I see that this point looks like 4 comma 1. So I can put in 4 comma 1 if I want. We change the colors. And there we go. So this is the function, right? So when we plot a piecewise defined function, you have one curve on the left-hand side and one curve on the right-hand side. In this case, they're straight lines, but straight lines are curves, kind of. So you have to do something like that to plot a piecewise defined function, but there you go. So that's what they look like. And the reason they're going to be kind of an issue for us, not an issue, but if you remember back to when we talked about limits in the first lecture, what we talked about was that there were one-sided limits. You could have a limit from the right or a limit from the left. And just looking at a graph of a piecewise defined function, you should understand that on the limit from the left, right, you're going to be up here at 4 comma, I guess, what's that, 14, I think. And down here, if you do a limit from the right, you're going to end up down here at 4 comma 1. right? So this is 4 comma 1, and this is like 4 comma 14, right? So the left-hand side and the right-hand side don't agree as to what the limit should be. And so when you evaluate limits with piecewise defined functions, you need to keep that in mind. So basically, you just need to worry about which piece you should be in, the left piece or the right piece. Or there could be 5 pieces and you have to figure out which one you're in. So let me just say this. So we're looking at the same example. F of x equals 3x plus 2 if x is less than 4. F of x equals 5 minus x if x is greater than or equal to 4, right? So if you were doing a limit from the left, if you were doing a limit from the left as x approaches 4, you're on the left-hand side, right? And so the first function here is the function you use on the left-hand side of 4. For the function f of x, if you want to limit from the right as x approaches 4, you would need the second function, because the second function is x greater than or equal to 4. So there's nothing unusual about piecewise defined functions. It's just that make sure you understand which piece you should be using based on the x value. Now it says if you wanted the two-sided limit as x approaches 4, you would need to check that the one-sided limits both give you the same number. Now we know they don't because we looked at the graph already, and they don't. The left-hand side's up at 14 and the right-hand side's down at 1, so they don't match up. But in theory, they could have done. And that's what you'll have to do for a piecewise defined function. I think we're going to do that for this one, so let's go ahead and do it. Please stop changing the page on me. It's really frustrating. Oops. Okay. So let's try to do this. So we're looking at that same function, f of x equals 3x plus 2, if x is less than 4. F of x is 5 minus x, if x is greater than or equal to 4. And we want 3 different limits. The left-hand limit, right? Remember the minus is left-hand. The limit as x approaches 4 from the right of f of x. The plus is right-hand limit. And the limit as x approaches 4, no plus or minus, that's the two-sided limit. So we have the one-sided limit from the left, the one-sided limit from the right, and the two-sided limit all at 4, which is the switchover point here. So what do we do? Basically what you do is very simple. Replace the f of x with the appropriate function. So when you do the limit as x approaches 4 from the left, replace this f of x with 3x plus 2. When you do the limit as x approaches 4 from the right, replace f of x with 5 minus x, because x is greater than or equal to 4 when you're on the right-hand side of 4. And when you do the limit as x approaches 4, the two-sided limit, well, you don't do anything. When you want the two-sided limit, you just look at the results from the previous one-sided limits. Okay? So this is what it would look like algebraically here. The limit as x approaches 4 from the left of f of x is the limit as x approaches 4 from the left of 3x plus 2, because we replaced f with 3x plus 2. When you get to this point right here, now you've got a continuous function, and for continuous functions, for polynomials, just plug in the 4. So you just put in the 4, and you get 3 times 4 plus 2, which is 14. Okay, so that's the one-sided limit from the left. Now you do the limit from the right. So when you do the limit as x approaches 4 from the right, you have to replace f with 5 minus x, which we've done. Limit x approaches 4 from the right of 5 minus x. This is a continuous function now, so just plug in 4. So you end up with 5 minus 4, which is 1. So the two one-sided limits are 14 and 1. And then you get down here to the limit as x approaches 4 of f of x, the two-sided limit, and the two-sided limit does not exist. It does not exist because remember what we said about two-sided limits in the first lecture. The two-sided limit only exists when these are the same number. So you can't have a 14 and a 1. If you had a 14 and a 14, then you'd say 14. If you had 1, if you had 1 and 1, then you'd say 1. But if you have 14 and 1, you've got nothing because they're not the same. Okay? And that's just what you see on the graph here, right? On the left-hand half, you end up at 14. On the right-hand half, you're down here at 1. Of course, this y value and this y value are different y values, so there is no limit. Now, not every piecewise defined function has this happen, because if you look at a formula like this, like 5 minus x, you can move this around, right? Like I can go like 7, move that up, or 8, 9, 10, 11, 12, right? Like I can just keep moving this. I can change the number here. And if I go like 16, right? Look how they almost match up now, right? If I can move it up a little bit more, right? If I move it up enough, 18 minus x, then look at that. They magically match up at 14. So if you can make the two pieces match up here, then even though we've got this piece here and this piece here, a left-hand half and a right-hand half, they happen to match up right here at 14. And so this, in this case, the limit would be 14. The left-hand limit would be 14, the right-hand limit would be 14, and the two-sided limit would also be 14. So just because it's piecewise does not mean that the limit does not exist. But you have to check it the way that we checked it here. Okay? So that's pretty much what I wanted to talk to, kind of like an introduction to analytically evaluating limits. Make sure you look over the section before the next lecture for sure, because we're going to be doing quite a bit more algebra in the next section. All right, so thanks for watching, and I will see you next time.